the study of the visible portion of the spectrum. So that's what we will do today. Can someone foresee the problem that may arise with photometry that does not necessarily arise with radiometry? So what was radiometry? Radiometry was the pure study of electromagnetic radiation, right? You use a detector for it, correct? For photometry, usually the detector is your eye. And what could go wrong when you use your eye? One thing would be a problem if somebody is colorblind. What about farsightedness and nearsightedness, right? So that becomes a problem. Yes, sir.
I have a question. So is it possible that we are all seeing different things?
Yes, absolutely. We all see different things.
And how do we know something is something? You know,
exactly. That's the problem. That's the problem with photometry. How do we know something is something? You view the world through what you observe, right? What you touch, what you feel, what you see. But everybody's sight is different. So how do you know the world that you observe is the same as the world I observe, is the same as the world Amanda observes or Lucas? Like, they're all different because we are observing the world through our senses. That's the problem with photometry. Also, what you observe during the daytime may be different from what you observe during the nighttime. Okay, so let's write this down. So photometry takes into account the response of the human eye to the radiant energy at various wavelengths. So we can say that it involves what is called psychophysical measurements. Issue. The human eye, when used as a detector, does not have a flat spectral response. What does that mean? It does not respond to all wavelengths with the same sensitivity. We're not even talking about the actual problems with people's eyes. I'm just saying that a normal 20/20 vision, a person who is not colorblind, a person who is perfectly normal, for a lack of a better word, will respond to different wavelengths differently. So how do I say that? Flat spectral response means that is the eye does not respond to all wavelengths with equal sensitivity. So for example, if the eye has blue, yellow, and red light incident on it at the same time, out of all of these, the yellow will appear the brightest. Equal intensities. In other words, when we use photometric quantities, we measure properties of light as they appear to the normal eye rather than as they appear to an unbiased detector. And when we talk about unbiased detectors, what field are we talking about? Radiometry. So, since not all human eyes are identical, we know that, right? And also, even if you start with the 20/20 vision, what happens when you're 40 or 45?
25.
Yeah, you start becoming, your eyes start, the muscles behind your eyes become weaker and it's hard to focus anymore. So your response keeps changing over time. Okay, so since not all human eyes are identical, what have we done? We have come up with what we call a standard response that was determined by the CIE, the International Commission on Illumination. In which the relative response or sensation of brightness for the eye is plotted as a function of wavelength. I'm going to be so proud of myself. Watch this.
Whoa.
This is what it looks like. Can anyone look up CIE? CIE.
Commission internationale d'illumination. Commission internationale d'illumination.
Good. Thank you. Okay. Everybody got that? So note what this is doing. This is what that graph is. This is what the commission was made for. So if you look on the graph, this graph is lambda on the bottom. So the wavelength goes this way, right? On this side, they have what is called luminous efficiency. And I'll explain that in a second. And on this side, they have a luminous flux. But if you notice, violet, blue, green, yellow, orange, and red. What is our eye most sensitive to? Yellow.
Hey, it's like the high point.
That's why it's the highest point.
Wow.
Woohoo! So this graph shows that the peak sensitivity is around yellow-green of lambda about 555 nanometers. So yellow-green. So lambda up about 555 nanometers. That's what our eyes are most sensitive to. However, do not be deceived, because this in fact changes between night and day. So what do we call those? When we observe this graph during daytime, the eyes are adapted to this graph, and it's called photopic vision. However, during the nighttime, this graph changes slightly. So lambda for this graph was what? 555 nanometers. During nighttime, this graph is shifted slightly towards the green end of the spectrum, peaking at 510 nanometers. And that one is called the, how do we say this? Scotopic vision. And it's shifted slightly towards the green. And this is towards more of the yellow part of the spectrum. So at night, it shifted slightly towards the green. So this whole curve, guys, right? This whole curve will be shifted towards the green. So the curve remains the same, it just gets shifted.